Okay, let's go and get started. Today we're going to look at review a couple things quickly, and then I'm going to go over some stuff that's going to be important for you to work on that lab. And primarily what I want you to do today is kind of watch the video, the lecture, and then start working on the lab. So you're going to have some lab time today. So don't squander that. Use that for lab 2, finishing that up, and then working on lab 3. Next week, we're going to get started on some new stuff, but let's go ahead and get to it and get through what we need to get through today. All right, so first off, quick review of the bitwise operators that we looked at last time. We had right shift, left shift, which basically takes these bits, moves them over by this number of positions, but does not modify that if it's a variable. Just like if that was a plus sign, it doesn't change this. We're just taking that bit pattern, moving it over, giving that as the result, or evaluating as, let's say it that way. It's evaluating as A, as if it were shifted left or right by this number of bits. Same thing with left. And then we have bitwise and, which basically if for each and every bit position in these two operands, if both of them are 1, we get a 1, otherwise we get a 0. Bitwise or, same thing for every bit position when those two are lined up. With or, if either one bit position or the other one, or either one operand or the other one in a certain bit position is a 1, we get a 1, otherwise we get a 0. XOR, it gives a 1 if the two are different from each other in a position. And then the inverse basically just flips all the 1s to 0s and all the 0s to 1s. Now, continuing the review from last time, we also had the modifying assignment versions of those, which basically are the same thing as saying A equal A, in this case shifted right by B. But if we do them this way, we can do all of that in one line and say A shifted right equal B. That actually does change the result of this. It takes it, shifts it by this many positions, and then puts it back into A. And the same thing for the other ones. Okay, now, for the lab, and just for general system programming kind of concepts, is this concept of bit masking. And bit masking uses bitwise operators to either set, meaning turn a bit from a 0 to a 1, or force a bit to be a 1, or to clear, meaning force a bit to a 0, in some binary representation of data. So if we have some variable that has some pattern of bits in it, we can use the bitwise operators to clear bits when we want to, force them to be 0, or we can use it to force them to be 1 when we want to. And essentially, the general way of using this is the bitwise and, that's used to clear bits or get rid of them, force them to 0. And bitwise or is used to do the opposite, to force certain bits in a pattern rather than to 0, force them to be 1. So the value used in that bitwise operation when we're doing bit masking is usually called the bitmask, or just the mask value, bitmask value. And so we might see those terminology somewhere like, okay, what's the mask value we need, or what's the bitmask for this? That's referring to the pattern we're going to use to force a bit to be off or force a bit to be on. All right, so let's start with and. So we use, like we said, we use the ampersand, the bitwise and, to clear bits. And let's look at the truth table to see how we can do that. So we want the bits to be cleared. So looking at this truth table, there's something interesting. So if we focus on operand B and look at only the positions where it has a 0, you'll notice the result. So if I look at that 0 and I look over to the result, so right over here, you'll notice that if I have a 0, I get a 0. If I have a 0, I get a 0. In both of the cases where this is 0, it pushes through the 0 into the result. Now, what about cases where there's a 1? Well, if we look at where there's a 1, what does it push through? Well, it pushes through a 0 when A is 0, and it pushes through a 1 when A is 1. So in other words, any positions that have a 1 in B will leave the A positions, those same positions in A, untouched. But any position in B where I have a 0, it'll force the result to have a 0. So the idea there is if we want to force some bit in A to be cleared, to be pushed to a 0, we just put a 0 in B, and then we do the and. The bit positions we want to leave untouched, we just put a 1 in those positions. All right, let's look at an example of that. That might make it a little more clear. All right, so looking at an example, here's some example code we have down here. So let's say we have this variable x. It's an unsigned character, so only 8 bits, although this would work on short ints, long. We could do this on other integer data types as well. But you'll notice we have this unsigned character. I'm just doing this so we can see the 8 bits really easily without a whole bunch of bits. And then I have my unsigned character mask. Now, unsigned character x is holding the value 200, and that's decimal right now. But to make it clear in the mask what pattern we're talking about, I used hex. So 80, if you remember back to that, that's a 1 in the most significant place, and then 0s everywhere else. So 80 in hex, from your perspective, looks like this. So 8 was 1, 0, 0, 0. That's a 1 in the 1, 2, 4, 8's place. And then this is all 0. So there's one bit that's actually set high, and all the rest of them are set low. So what that's going to do in this code, it's going to isolate just that most significant bit. So if I AND X with the mask, in other words, I'm taking that value 200, which has its own bit pattern, and I'm ANDing it with mask, I'm forcing to 0 all of the bits except for that most significant one that's on this end. So that way, if this winds up being non-zero, then we know that most significant bit was 1. If it winds up being 0, we know that most significant bit was 0 because we've isolated just that one bit. We've forced all the other ones to 0. The only one we have is that one. Now let's look at that in bit terms to get a little bit better feel for it. So this is 200. 200 turns out to be the same as C8 in hex, but it looks like this: 1, 1, 0, 0, 1, 0, 0, 0. And then here's the 80 we had from there, which is 128 in decimal. But if we look at that, it's a 1 followed by 7 zeros. And now when we AND those, notice that all of these bits here, no matter what they had, there was a 0 there, so that forces the output to be 0. But there's a 1 here in what was B earlier in the second thing, so that's going to pass this 1 through. So 1, when this drops down, if it sees a 1, it passes through. When it drops down, if it sees a 0, it gets blocked and forces a 0. So we're going to get 80. So that result of 80 hex or 128 passing through now shows the most significant bit had a value of 1. Okay, so that's how we can use AND to clear bits. And really, we don't have to do them one at a time. You could put multiple bits in this up here and pass more than one through. Or we could mask out just one of them like we did here. Or mask on one of them and mask out the rest, I guess we should say. All right, now let's look at using OR to set bits. So remember, AND was used to clear bits. OR is going to be used to set bits. And again, let's take a look at the truth table. So over here, let's focus on B. So notice when B has a 0, or let's look at the 1 first. When B has a 1, what happens over here to the result? We always get a 1. But when B has a 0, it passes A through. So it's very similar to what AND does, but what it's doing is it's passing through, forcing 1s through wherever B is a 1, and it's passing through whatever was over here whenever B was a 0. So to force a bit in A to be set, we just put a 1 in B, and to leave it untouched, we put a 0 in B. All right, let's look at an example for that one. Okay, so let's say we want to set the value of the most significant bit. We want to force that most significant bit to be high, whatever it is. We don't care what it is, we just want to force it to be high. So here's my mask. Again, my mask is the most significant bit. So I'm going to push that onto whatever this pattern is and force a 1 into that position. And the way we can do that is, in this case, I'm actually changing the value of x because I'm taking that variable and I'm forcing that bit high. So notice I can do x ORed with a mask. That's going to force that 1 bit high. And then I'm putting it back into x, or we could have used the modifying assignment version of that down here with OR equal. That works as well. And then I just print it out. Now let's look at the bits of that. So again, here's what 100 looks like in hex, 64 hex. And then if I put this as my mask pattern, notice that, remember what the bitwise OR did. If it's a 0, it passes it through. If it's a 1, it forces it to be 1. So they were forcing that to be high, leaving the rest of the pattern untouched. So our result is going to look exactly like that. All right. So these are actually really powerful things, especially for systems programming related things where you're dealing with registers in memory or some sort of configuration where there's a file and there's a byte and some part of it means one thing and another part means another thing, or you're dealing with what are called bit fields where you have this a whole bunch of bits and some of them they're divided into groups and you deal with this all the time. So for example, if you're writing some sort of hardware driver for something like a wireless module on a embedded system, that wireless module is going to have kind of bit patterns that need to be put into certain parts of certain bits, and you can use these masking operations to then clear part or add things in. In some cases, you can use them in combination, like clear out these low 4 bits and then add a new pattern in over the top of that. So you'd use AND to clear out bits, and then use OR to add in a new pattern in that spot. And the cool thing about this, these operands, remember we talked about C language being kind of this lower level language, that really this bitwise OR, most microprocessors have a bitwise OR operation built in. So remember we talked about there being a one-to-one correspondence between the C language operations or operators and the microprocessor. That's what we see here, is it's kind of allowing us to use that. So we don't have to use some more complicated mathematical way to manipulate the bits. We just use these bitwise operators. Okay, now one other thing that's related to this is that there's a technique where you can use the shift bitwise operators to modify the bit mask. So in other words, that can be useful for moving some mask bit across some range of bits. So the one we just did with the most significant bit being like over here, what if you wanted that to go from that position one time through a loop, and the next time through the loop you wanted to make it be this bit, and the next time that one, and the next time that one, and you want to ripple through kind of the entire byte or int or whatever it is. And so that's where shifting can come in useful. So here notice I have this unsigned character mask. I have this for loop that goes through 8 times. And you'll notice what I'm doing is every time I'm saying mask shifted right equal 1. That says take the mask, which is 80 right now, move it over 1 bit, and then go back to the top of the loop. So we would use the mask for something here on the most significant bit. We would then shift the mask, and then the next time through the loop we're on the next to most significant bit, or bit 6. And the next time through the loop would be on bit 5, and then 4, and then 3. And this would go through all the way down till we're on the one place, the bit 0. And so this can actually be really useful when used in conjunction with masking. Now let's just take a quick look at the pattern that we get when we do that. So here's that same code we had from the previous slide. But here it is. There's what the mask would look like for each iteration of the loop I. This is not the output. This is just the mask value. So for iteration 0 through the loop, the mask looks like 80 because we haven't changed it yet. The next time through the loop, it's moved over 1 space because we shifted it by 1. And then the next time here and there and there, and we just work our way all the way across. So this would let us, if we wanted to, isolate each of the bits individually and say, is this one a 0 or not? Is it a 1? Is this one a 0 or is it a 1? Is this one a 0 or is it a 1? And so you could use that in a number of ways. And that's going to be, notice you could also have a mask on this end where the mask starts with a 1 here and you shift it the other way. Just using shift right, just use shift left equal 1. And then we could make it ripple across the other way. And that can be really useful for systems programming tasks where we need to take something that's in a group of bits and then isolate them and look at them one at a time for some reason. And as we'll see when we take a quick look at the lab, that might be something you want to do for the lab as well. And so just keep that in mind. And here I'm going to, this is kind of at a bad angle right now. I usually have it lifted up some. But anyway, we're almost done, so we'll just power through the rest of it. All right, so let's take a quick look at the lab. And that's going to be something that's going to, we'll just talk briefly about, and then I'll let you loose to work on it. Okay, so here's the lab. So notice for this lab, you're going to write this program that I have kind of described down here below. So you're going to have a main, and what it's going to do is it's going to call this function to print out a table of the characters that should say from A to Z. I'll fix that before I post it. And then the print table function, basically you pass in a start character and an end character. And when you pass in that start character and that end character, it's going to then create a table, which we'll look at what that looks like in a second, but it's going to print out the decimal representation, the character representation, and the 8-bit binary representation, and the hexadecimal representation. So it's going to basically print a table. And let's just scroll down quickly and look at what that table looks like. So here's what the table looks like. 65. So if we called the function and said go from A to Z, it should print out a thing that looks like this. So 65 is the letter A, and here's bin, the binary representation, and here's the hex representation. Now, something that's going to be important for you solving this problem is, first off, %C. We've done stuff with printf, just like we did back in our examples on the thing today, and you might have noticed those % things like %D is the decimal integer format specifier. Well, you would use %D to get the 65, but how do you get a character like this to show up? Well, you would use %C for the character. So %D for the number, decimal integers, %C for a single character. And then for this binary thing, though, there is no binary print specifier. You're going to have to write code, which is actually what this print binary function is going to do. You're going to pass the number you want printed. So in this case, you'd pass, for example, 65 into that. And what it's going to do is it's going to print this out 1 bit at a time. Now, how do we get 1 bit at a time? Well, we're from the number 65. Well, think about that, what we just talked about with the masking, where if we started the mask all the way at the most significant, we could say, is that bit 0 or not? And if it's 0, we print F as 0. If it's not, we print F of 1, and then we go to the next bit, and we move the mask over, and then go to the next time in the loop and look at that bit. Is it a 0 or not? Is it a 0? And we basically just print all those out individually, and as long as you don't do a new line, a \n on the end of those prints, they'll all get run together like that. Now, you don't need to have an array or anything like that. You can just have a loop that goes through, very similar to what we had in the lecture. Put that in. Check to see, and have an if statement that then uses that mask value to see if the bit is higher or not. Now, how do you isolate a bit? That's going to be forcing every bit to 0 except that one. I'll leave it up to you to figure out whether to use and or for that. And then the last one, to print out the hex number. Actually, there's a printf modifier for that, %x. You might want to Google that and look at some examples. One other thing that I want you to remember is when you make and call this loop, so for example, to go from A to Z, remember, you can actually call that function, the print table function, and pass to it single quote A, single quote, and single quote Z, single quote. You can pass those in just like you see them right here. So you can put that in for the function parameter. And the reason for that is, remember that the capital A in single quotes evaluates as the character value of that character, which in this case would be 65, which is where we wanted to start. And then the Z is going to evaluate as 90, just like we see down here. But it can make your code more readable, because we would say print table A, comma, Z, rather than 65 and 90. So I would go ahead and do that if I were you as well. All right, so really that's all you have to do for your program. Make sure it looks like this. And test it with other ranges of numbers as well, like maybe use lowercase a and lowercase z, or capital A to lowercase z, or space. You can put a space in here and go to lowercase z, however you want to test that. I would make sure, and maybe you just go A through F, but your table should look like this. Now, one thing you are not allowed to do is you're not allowed to just hard code it and have a print statement that just prints all this stuff out down here. You have to have a loop. You have to have these functions. They have to work correctly. It needs to be organized like this. Now, one final word of advice is it needs to compile and execute, and it needs to compile and have no warnings or errors. If you have an error, it won't really compile, but if you have warnings, I'm going to take off points. Now, one of the things that I noticed you're probably not used to doing is if you organize your code this way, where the main is up here and it's making a call to the print table function, which is making calls to print binary and print hex, you need to have function prototypes up here at the top. And to remember what a function prototype is, it's basically like a line of code that tells the compiler what the call signature is of a function that's going to be used later on in the program. And so to do that, what I would do is you just copy this line. Oops, I don't know if I can copy that line of code there. Leave it here in the function, but also copy it, put it above the main, and just stick a semicolon at the end, and that becomes what's called the function prototype. In other words, when the compiler reads this program from top to bottom, so when it's reading that from top to bottom, it's going to say, okay, there's going to be a print table function, and I know what the parameter types it's going to pass, how many of them there are, and I know the type it's going to return. And all of these are just void returns because they're just printing things. But the compiler needs to know what a function looks like, how many parameters it accepts, how many it accepts, and what it returns to make sure it's being used right when we use it up here. And the only way to make sure it's defined before we see it being used is to put a function prototype up here. Or you could also define the functions above the main. So you could take all of these, put them before the main. That would work as well. The general practice, though, is to keep the main towards the top and just put the function prototypes up here. So that way when you open a program, you see what the main function is without having to wade through a bunch of other functions. And notice that's a little bit different than in Python. In Python, you have to define those functions at the top, either directly or by importing something. In C, you don't really have to. You can put them down below, but if you do put them down below, you need a function prototype for every one of those functions to be defined before it's actually used. Okay, let's switch back to the slides for just a second. Oops. Okay, so that's everything for today. Work on either Lab 2 or Lab 3. Try to get those underway or done. There's really not a lot of code you need for really either of those, so you shouldn't really have too much. It shouldn't be a lack of time. But if you are working on those and you get stuck or something doesn't seem right to you, or you're getting errors or warnings and you don't know why, remember to send me a text message, send me an email, either on my Gmail or on the Shawnee account. Send me a message on Discord, however you want to get a hold of me, and I'll see if I can help. And if you get really stuck, then I can always come in and sit down with you, and we'll take a look together. My office here. I'm in the conference room in my office here in my building. I'm on 2nd Street, just like the university is. I can actually see the university if I look out the window over there. So what I would ask you to do is message me. If you get out, we'll see if we can answer it. And if it seems like it's still confusing, I'll come in and I'll sit down with you. But if you do come in, make sure to be safe. Make sure to bring a mask, and we'll go to a classroom somewhere where there's plenty of space, and we'll see what we can do to figure it out. Okay, that's it for today. Get to work. Have a good weekend. I'll see you guys next week.